In this video, we will talk about blood cell production and go into red blood cells as well. So this will be a slightly longer video than some of your other ones because it has sort of more stuff to cover. But this starts on slide 18 on your PowerPoint, and it starts at number 11 on the notes. Okay, it says, what does hemopoiesis mean? You do see this suffix poiesis used from time to time in A&P, and what that means is it means production or the making of or creation of. Okay, so it comes from an ancient word that means production or creation or making. And then hemo is what we use for blood. You'll actually see hemo. You might see hema, or you may even see hemato or hemato. People pronounce it different ways. So all those basically mean the same thing. So you might see hematopoiesis or hematopoiesis as another description or another word to talk about this process. So all those mean the same thing, blood. But poiesis is the production of your formed elements, so hemopoiesis. So you're talking about your red blood cells. Remember what your formed elements are. They're your red blood cells, white blood cells, and platelets. And now all of these guys are made in your bone marrow, more specifically in your red bone marrow. If you go back to AMP1, there's two types of bone marrow. You got yellow bone marrow, which is where you store fat, and then you have red bone marrow, where you produce your formed elements, your blood. And so these are your blood making stations, so to speak. Now, as you get older, you have a lot of yellow bone marrow as you store fat throughout your life, but there's still blood making stations in different parts of your body, and most of them are on the axial skeleton. Like you have red bone marrow in your skull bones, you have red bone marrow in your sternum and ribs, you've got red bone marrow in your spine. You also have them in the hips, okay, which are part of the appendicular skeleton. And then you also have them at the proximal end, so close to the shoulder and close to the hips. But you have them on the proximal end of your humerus in your arm and your femur down in your thigh. And so you can look at if you would search for red bone marrow, then you can see some of the places in your body where you make your blood. Red bone marrow. You got images, and it kind of shows you there. There's a nice little picture of red bone marrow. Here you go. So there's a little picture there where you can see where your blood making stations are. So you do make some blood in your elbows and your knees as well, but you can see that most of it is there on the main axis of your body. Now, including the girdles, the scapula, the clavicle, the pectoral girdle, and then the pelvic girdle or the hips. You also make blood in those areas as well. Now, inside there, so inside your red bone marrow, and by the way, get used to this word, and I put it on your notes. Okay, remember that whenever you have multiple names for the same body part, it's good to learn both. Okay. You will also see in certain situations and in certain stories, you'll see red bone marrow also called myeloid tissue. Okay, and so I put that there on number 11 in part C. I put that it occurs in the red bone marrow, also known as myeloid tissue. And so get used to both of those. And I will ask you about that on the test. What's another name for red bone marrow? Because some books and some stories and some videos you watch will call it myeloid tissue instead of red bone marrow. And so there inside your red bone marrow, there are these stem cells. And these guys they have the ability to change. The word we use is differentiate. Differentiate is when a cell becomes a specific kind of cell. So when you have a stem cell is what we call undifferentiated. It can become different things. At least if it's a embryonic stem cell, or if it's what we call a pluripotent stem cell. Pluripotent means it has the potential to form many different kinds of cells. Okay, pluri means plural, and potent means potential. So you can take these cells and, given, depending on what signals they receive from the body, or what signals you give them, if you're doing research or whatever, if you give them certain signals like hormones or other signaling molecules, you can coax these cells to become whatever you want, so to speak. And so these guys that are in your bone marrow, they can become all three types of formed elements. They can become red blood cells. They can lead to the cells that produce platelets, or they can become white blood cells. And we call those guys hemocytoblast. Whenever you see the suffix blast, that will indicate a stem cell. It basically indicates an undifferentiated cell. And it's going to, it's always at the end of a word. Okay, well, usually anyways. But when it's at the end of the word, it'll eventually become what's in front of it. Okay, so hemocytoblast, the blast tells you it's a stem cell, and it's going to become your blood cells, hemocytes. Okay, so that's another word we use for formed elements. Is you also hear them called blood cells, but I'll explain why I don't like that word too much. I'd rather call them formed elements, because two of them are technically not cells. Okay. But hemocytoblasts are the stem cells that are in your bone marrow, and they can differentiate, they can change into all types of formed elements depending on what signals they're receiving. So hormones do come into play, and then you got these other signals that are called colony stimulating factors, or CSFs. Okay, and you'll hear about those guys with hospital setting blood work and MLT classes and stuff like that. You'll probably hear about colony stimulating factors. They basically, CSFs basically coax the hemocytoblast into becoming a particular type of cell. And so I'm gonna blow up this picture here and kind of show you what we're talking about. And so you got the original cell up here at the top. That's the hemocytoblast. That's the stem cell right there. And depending on what he receives, so you can see the CSF coaxing going on right there. So he can differentiate first into these two types of stem cells. And then depending on what stimulating factors he receives, he can become a red blood cell, or he can become the cell that will eventually form platelets, or he can differentiate into these white blood cells over here. Now, the final result, okay, the final result is down here at the bottom. Those are your different types of formed elements. You got red blood cells first here, you got platelets there, and then all these guys over here are different types of white blood cells. And we get into those different types of white blood cells, both in this chapter and also later on with the immune system. So you start off with that original cell, the hemocytoblast, and depending on what colony stimulating factors is received by the bone marrow, and if you go down a little bit further, what hormones are received by the bone marrow, that will coax them into becoming a particular cell. So your cell makes more red blood, or your bone marrow makes more red blood cells when necessary. It'll make more platelets when it needs to, or it'll make more white blood cells when it needs to. It just depends on what signals it's receiving. Now, to be more specific, if you're talking about just the production of red blood cells, which will be over here. So the production of red blood cells includes those guys there. So you go here to here, and then there to there, and then you make your red blood cells. That's called erythropoiesis. So erythro means red blood cells. So erythropoiesis means the formation or the production of red blood cells. We're going to get into that. If you're going to make platelets, then it's going to go from here to here, and then it's going to go down this way. And eventually you get to this guy called a megakaryocyte. And then what he does is he pinches off little pieces of himself, and that's what platelets are. Platelets are not cells. Platelets are pieces of cells. And then if you're going to make white blood cells, it depends on what type of white blood cell you're going to make. You can go this way and then come down here and then make these different ones. or you can go the other way, make this cell, and then make these guys down here. All right, so your bone marrow is always adjusting to what the body's telling it to make through those stimulating factors and through those hormones. If you're talking about white blood cell formation, they call that leukopoiesis. Leuko means white. And then thrombo is the prefix we like to use for clots and platelets, because platelets are involved with blood clotting. So you have what's called thrombopoiesis, which is the production of platelets. But we're going to talk about first red blood cells, and then we'll get into white blood cells and platelets further on down in the chapter. So erythrocytes is our fancy term for white blood cells. Erythro means red, cyte means cell, okay? So erythrocytes and red blood cells, they here's some of the characteristics. Now, one of the things I want to make note of is this right here, okay? When a red blood cell is maturing, it loses all of its internal organelles. Okay, go back to AMP1. A typical cell is going to have a nucleus, and it's going to have other organelles in its cytoplasm, like your ribosomes and your endoplasmic reticulum and your Golgi apparatus and your mitochondria and all those guys that are inside of a cell. Well, during the maturation process of a red blood cells, all those organelles degrade away. Okay, they break down and basically disappear. And so a mature red blood cell is technically not a cell by biological definition, because it doesn't have a nucleus and it doesn't have other organelles. But what the cell's doing basically is it's getting rid of everything that it doesn't really need. Okay, red blood cells, their primary job is down here. Okay, transport oxygen. That's their job. Now, in order to transport oxygen, they need a protein, and that protein's called hemoglobin. So think about it. The more hemoglobin you have, the more oxygen you can transport. And so what the cell does is basically clear out everything else, and that way it can pack as much hemoglobin as possible inside of it, so it can be as good as it can possibly be at transporting oxygen. And you actually see that with us. Like if you're going to go on a long trip and you got to pack your car, you got to pack your car with as much clothes and other stuff that you can. The first thing you do before you pack your car, the first thing you do is clean out your car. You clean out all the unnecessary things, or the things that you're not taking with you on the trip. You get all that stuff out of the way, and that way you have more room to pack what you're going to take on your trip. And that's kind of what red blood cells do as well. They lose all of their internal structures that kind of just take up space, and that way they can pack as much hemoglobin as possible inside of them. In fact, this number is pretty crazy right here. One red blood cell can have about 280 million hemoglobin molecules inside of it. With blood, you get crazy numbers. Like earlier, you had, one drop of blood can have 5 million red blood cells. Every one of those 5 million red blood cells can have 280 million hemoglobin proteins. And so the numbers just get outright crazy. But the oxygen carrying capacity of the blood is incredible because of its ability to pack as much hemoglobin as possible inside of it. The other thing that makes red blood cells really good at transporting oxygen is its shape. Okay, the word is biconcave. Concave means that it bends in. Okay, so a concave surface is kind of like a caved in surface. It's bent in. Biconcave means that it bends in on both sides. And that's actually what produces that characteristic divot that you see in the middle of a red blood cell. It looks like the middle of the cell is sunken in a little bit. That's because it's bending in on both sides. Now, what that does is it shortens the distance that things have to travel to get in and go out. Okay, so when you're talking about diffusion, it basically shortens the distance of diffusion. So that way, when a red blood cell goes through a tissue, the oxygen will very quickly be soaked up, so to speak, by the hemoglobin. And so it just makes it easier to pick things up and drop things off. And so that biconcave shape is very important. And whenever a red blood cell loses its biconcave shape, then that affects its ability to efficiently pick up and drop off respiratory gases. The other thing that's kind of interesting about red blood cells is when they move through a capillary bed. Capillaries are extremely small. Okay, they're like the width of a human hair. You know, that's kind of how they usually describe it. It's like, you know, it's like actually thinner. You know, the capillary can actually be thinner than the width of a hair on your head. And so the hole, you know, the tunnel to go through in the capillary is very small, and red blood cells are just small enough to fit through a capillary bed. But they can't go in two at a time or three at a time. If you're a NASCAR fan, they can't go in three wide, you know, into a capillary bed. They have to go in single file, one at a time, and they kind of go in one right after another. So it's kind of like, once again, if you're a NASCAR fan, it's kind of like they're drafting. You know, they're going in one after another, and you'll get this chain of red blood cells sort of moving with each other, one right after another. And they actually say that it looks like a stack of coins. And that's what it looks like down here in this bottom picture. You can see down here that it looks kind of like a stack of quarters right here and right here on this picture. And so that right there actually has a name. So when you see that, this single file looking movement of red blood cells, let me blow it up there. That right there is called a rouleau, which is French for roller. Okay, they're talking about a a roller maybe you use to thin something out, like what am I thinking of? The thing in the kitchen, you know, the kitchen roller that you use to smooth out bread. But it also can mean a roll of coins, like you would get. You know, we've all seen a roll of quarters. You know, so when you take the roll of quarters out, they're stacked on top of each other, and it looks like that right there. So rouleau kind of means roller or stack of coins. And what's cool is if you go onto YouTube, you can actually watch videos of this happening. If you type in something like erythrocytes moving through a capillary bed, you will get some, you know, animations, but this right here is an actual video of a capillary bed, and what you'll see. Oh, I got to push play. Sorry. All right. So what you see here is you see red blood cells moving through a capillary bed. Okay. So you see two capillaries joining there. It makes a slightly bigger vessel. And then these guys are going to travel up, and then eventually they're going to deposit into a bigger vessel, which would be a small vein. In a small vein, we call a venule. Okay. So the red blood cells are coming in through here, and then they're making their way up, and they're eventually going to join this bigger stream, so to speak. So this kind of reminds me of like streams feeding into a river. And if you watch it, let me undo the drawing here and kind of show you what's going on. Look at the red blood cells that are in the capillary bed, and you can see that they're moving sort of one right after another in this assembly line. Now here you can be three or four wide. That's a bigger vessel. That's a venule. That's a small vein. But you can see here with the capillary that they have to kind of move one right after another. They can't go in two wide or three wide. And if you pause it in a couple places, it actually does resemble a stack of coins. And so, right, I'm trying to figure out, yeah, right here. Look right there, and you can see that these 5 red blood cells right there are just stacked one on top of each other, and it resembles a roll of quarters as it makes its way through. And so that's really cool looking there. Just showing you. Now, another thing you notice, okay, let's back up for a second with the video. Notice how much slower they're moving through the capillary versus the venule up here. Okay, because of the small size, they have to go through slowly as well. And by going through slowly, that actually gives them more time to do what they need to do. And so they can very efficiently drop off oxygen and pick up the carbon dioxide if that's what they're going to do as they move through the capillary bed. So also this single file movement also slows them down. And that also makes them more efficient to doing what they need to do, dropping off oxygen. Okay. And so, or if this is the lungs right here, they're actually picking up oxygen. So we'll mention that a little bit later. And there's another video which is kind of cool. That right there is a capillary feeding into a vein. But you can also find a video of right here. This is an artery feeding into a capillary bed. Okay, so right here, this down here is a small artery. That's called an arteriole, a small artery. And so the blood's actually coming in and going into these three capillaries right there. And what you'll notice is that as it starts making its way through the capillary bed, it slows it down. So let me clear my drawings here, and you can see how much slower the blood's moving. See how much slower the blood's moving through the capillaries versus that small artery. And that's also, oh, that's beautiful right there. There's the stack of coins right here. There's the rouleau, is what we call it. And so that's sort of how capillaries work. Is they're going to slow down the movement of blood, and that way each red blood cell can efficiently pick up and drop off oxygen depending on which part of the body it is in, because that's the primary role of a red blood cell, is to pick up oxygen in one place, the lungs, and then drop off oxygen at the tissues. It can, but we'll talk about this later, but red blood cells can transport carbon dioxide. That's just not their main function. Their main function is oxygen. We'll actually learn later that they actually most of the carbon dioxide that's being transported in your blood is not being transported by red blood cells. It's actually being transported in the form of a substance called bicarbonate, and that's going to come a little bit later in the semester. So let's not worry about that right now. Let's just kind of associate red blood cells with the transportation of oxygen. Now, inside the red blood cell is a protein called hemoglobin, and that's actually what makes blood red. That's what makes red blood cells red, and it's what makes blood red. And this is the guy who can change color. So this protein is changing color depending on if it's bound to oxygen or not. And so you'll hear the words oxygenated and deoxygenated. And I would rather you, as a teacher, I'd rather you use the term oxygenated than the word oxygen rich. Okay, oxygen rich, and it's not so much that one. It's the other one. I would much rather you use deoxygenated blood than oxygen poor blood, because even deoxygenated blood still has a good bit of oxygen in it. Okay, it could still be 70% saturated with oxygen. And so when you say oxygen poor, it makes you think there's hardly any oxygen. That's not the case. There's just less oxygen than there was. Okay, so oxygenated and deoxygenated is a better way to describe blood instead of oxygen rich and oxygen poor. It's just more accurate. Okay. Now a hemoglobin molecule. So let's go to a hemoglobin molecule, which is down here. So here's a hemoglobin molecule, and it actually consists of 4 subunits. Okay, 4 protein subunits. 2 of them, which are dark in this picture, 2 of them are called alpha globin. And then the lighter colored proteins on this picture, those are the other 2. Those are called beta globin. And beta globin is the guy you hear about with sickle cell anemia. People that have sickle cell anemia, they can't produce beta globin the way that it's supposed to be produced. And it basically cuts in half their ability to transport oxygen. Because what happens is, in each one of these protein subunits, there is a molecule with iron in the middle. So this right here is a picture of the molecule there. That's called a heme group. Okay, a heme group. And in this picture here, they put it looks like a little planet, like Saturn, with a little ring around it. And you see it represented like that a lot. But this right here is a heme group. Each subunit, each protein subunit has a heme group. Okay, and that is that's what oxygen binds to. It binds to the heme group, and more specifically, oxygen binds to iron because oxygen has a negative charge, or it's actually nonpolar, but the positively charged iron has 2 places there. It's 2+. And so the iron actually will bind with the oxygen. And it's not a strong binding. It's kind of weak. And it mentions that in the previous slide right here. It says binding is fairly weak. Basically, it'll grab oxygen in the lungs, and then it has to take it to the tissues and let go of it. And we talk later in the respiratory system what causes him to pick up oxygen and what causes him to let go. Okay, but the binding is fairly weak. Okay, carbon dioxide doesn't bind with the heme group. And if you look at your notes, it's on number 14, part C. I actually made a typo. If you look at 14C, it says each heme group combined to one oxygen and or carbon dioxide. That's actually wrong. The first part's correct. Each heme group combined to one oxygen. But the notes actually should stop there. You should mark out where it says and or carbon dioxide, because carbon dioxide does not bind to the heme group. Carbon dioxide doesn't, it binds to the protein subunit. So when you're looking at a hemoglobin right here, the oxygen is going to bind here. The O2 binds to the heme group. Where's that heme group there? And then you have there. So he's carrying 4. CO2 actually binds to the protein subunit. So they don't compete. That's the word we use. They don't compete with each other for the heme group. And so O2 binds to the iron, and then CO2 binds to the protein out here. And so a hemoglobin molecule can carry 4 oxygens and 4 carbon dioxides at the same time if it has to. Okay, so one hemoglobin can carry 4 oxygens, and if it has to, it can also carry 4 carbon dioxides simultaneously, because there's no competition. Now, when you talk about competition in the body, it's usually for like a binding site or for something that the substances interact with. So imagine you have a binding site, like maybe this is a receptor here, and you have substance A and substance B. If they are competing for that binding site, if A binds, then B can't. Okay, we call that competition. And in fact, a lot of drugs work that way. They purposely bind to a receptor and they block a substance from binding that would have. Okay, so that's kind of like competition. You're competing for the same binding site. Well, CO2 does not compete with oxygen for the iron. Okay, so here's iron. Imagine he has a binding site here. O2's here, CO2 is there. Oxygen binds to the iron, CO2 binds somewhere else. Okay, so they don't directly compete for the iron. But there is a substance out there that does directly compete with oxygen for iron, and that is carbon monoxide. Okay, so now we're talking about not CO2, we're talking about CO. Now, CO does compete with oxygen for the iron. And if CO, carbon monoxide, if it binds to the iron, that means oxygen can't, which means oxygen can't be transported to where it needs to go. And that's where carbon monoxide poisoning comes into play. If somebody inhales carbon monoxide, it's going to go into their lungs, it's going to go into their blood, it'll go into the red blood cells, and it will bind to iron. And if it binds to iron, oxygen can't, which means that person is going to have decreased oxygen transport. And a lot of times the first cells to go is your nerves, because nerves sort of burn through oxygen. They crave oxygen. And so if you cut off blood flow or if you cut off oxygen supply to a nerve, it'll die very quickly. And you see that in stuff like strokes, or you see that when somebody gets choked. When you cut off the carotid artery going to the brain, and if the brain's not receiving oxygen, then they'll very quickly lose consciousness. And so that's what happens a lot with carbon monoxide poisoning, is they'll lose consciousness quickly, and then they can't get away. They can't get away from the gas, and so they pass out and they keep breathing in the gas, and then eventually that lack of oxygen is going to cause organ failure and cause them to die. And so carbon monoxide poisoning is something that's very dangerous. You can't see it or smell it, so you have to use detectors to even know it's there. But a lot of machines put it off in their exhaust, and you hear about it with cars. Like right now, it's very cold outside. You got to be careful about warming up your car in an enclosed area because the exhaust from the car has carbon monoxide in it. So if you go into your garage and you turn on the car and you let it warm up, it's pumping out carbon monoxide into the room. And if that gas has no place to go, then it's going to build up. And there's many stories of people who have accidentally killed themselves with carbon monoxide due to things like that, either running a heater in an enclosed area or a machine breaks and they don't know that it's releasing carbon monoxide and they breathe it in, they die. Or car exhaust. If you breathe in a lot of car exhaust, if something clogs up your tailpipe, and that car exhaust will back up into your car, and you can breathe it in the cab, and that can kill you. And so it's one of those dangerous things. But this is the idea behind carbon monoxide poisoning. It's going to block your ability to transport oxygen. Not only does it bind to iron, but it actually sticks to it. It actually has a greater affinity for iron than oxygen. So oxygen will bind and let go and bind and let go. CO2, or I'm sorry, CO, carbon monoxide, it'll bind and stick to the iron and not let go. And so really the only way you can, get it off is to get away from it for a period of time, and eventually it will let go, but it just stays stuck to it. And as long as it's stuck to the iron, then you can't transport oxygen the way you're supposed to. And so that's the idea behind carbon monoxide poisoning. All right. There's a hormone. I know you guys probably thought you were done with hormones, but you're not. EPO, erythropoietin, it's right there in its name. Okay, remember poiesis means production of. So erythropoietin causes the production of red blood cells. All right, erythropoietin. EPO is the common way that we shorten it up. This hormone is produced primarily in the kidneys. Okay, the trigger is low oxygen in the blood. We call it hypoxemia. So as the blood's going into your kidneys to be filtered, your kidneys are checking the oxygen content. And if they notice the oxygen content is low, then they will release EPO, and it's going to go to your bone marrow, and it's going to stimulate red blood cell production. So this is another hormone that you need to know for the first test. It's not going to be on the quiz or anything, but it's going to be on the test. It's called EPO, and on number 16 in your notes, I put the trigger and the source and the target and the effect. Trigger is low oxygen levels. Hypoxemia is the word we use. And the source is the kidneys primarily. It's going to go to the bone marrow, and it's going to stimulate red blood cell production. Then the more red blood cells you have, the more oxygen you can transport. Now that's why men typically have a higher hematocrit count, is because testosterone stimulates EPO, and EPO stimulates a higher hematocrit percentage, more red blood cells. And then you also have certain things that will naturally stimulate a higher level of red blood cells. One is high altitudes. There's less oxygen available at high altitudes. And so if you train for an Olympic event or whatever at high altitudes, it'll actually naturally boost your EPO production, and it will naturally boost your red blood cell production. It makes you better at using oxygen. So a lot of athletes will purposely train at high altitudes to stimulate their EPO levels, to raise their EPO levels and to raise their red blood cell percentage. Then they come back down to sea level where there's more oxygen for the actual event. And now they have more oxygen available, and they have more red blood cells to use that oxygen. So it makes them better at endurance. Okay, so a lot of your endurance sports where you have to do something for a long period of time, a lot of the endurance sports, if you get tired, you're going to lose. You could be talking about marathon running. You could be talking about Olympic bicycling or Tour de France bicycling. You could be talking about long distance swimming or triathlons or something like that. You could be talking about fights because a lot of times you may be a better fighter than the other person, but if you get tired, you could very easily lose that fight. They call it, gassing or running out of gas and that sort of thing, huffing and puffing, or you'll hear it called blowing up. Basically you can't, you run out of gas and you get tired, and then you lose the event. That happens quite a bit. So what people will do is they will try to stimulate their oxygen use. They try to improve it by purposely training at high altitudes. But another thing they do is they will cheat, and that's the blood doping deal. Some athletes will do blood doping. One of the things they'll do is they'll remove blood before the event. They'll remove blood. That will stimulate EPO production, and that will get them more red blood cells. Then they turn around and put the old blood back in their body before the competition. So now they have even more red blood cells, and they're even better at using oxygen. Or they'll just flat out inject themselves with EPO. And that's actually what Lance Armstrong got busted for. They found his DNA on a syringe. In the syringe was EPO residue, and that's the final thing that he got busted for. He denied for years, and they always had suspicions that he was doing things, but he was doing the blood transfusions. He was doing the injection of EPO. But then they finally got their hands on a needle that had his DNA on it, and that's when he finally went, "Yes, I did it." Actually, if you watch his Oprah interview, which I did put in Blackboard, if you go into Blackboard and go into the cardiovascular folder, down at the bottom is a video of Lance Armstrong giving his first confession of using performance enhancing drugs. So him and Oprah had a very famous interview where he had been denying for years and years and years that he did not dope, he did not cheat, he did not. Then they finally busted him with EPO, and he was like, okay. So he schedules an interview with Oprah, and at the beginning of it, you can watch it. At the beginning of it, she says, "Now we agreed that I can ask you anything. I can ask you anything, and you will answer truthfully." And he said yes. So her first question was, did you cheat? Did you use performance enhancing substances to cheat at cycling? Yada, yada, yada. He said yes. And that was the first time he had ever said, I did it. And so it was a big deal because, he was denying and denying for a long, long time. He's making millions and millions and millions of dollars off of this cheating, basically. So it was a big deal when he said yes for the first time. The second question she asked him, so she asked him, did you cheat? He said yes. The second question was one of those substances EPO? So the second question was EPO, because that's what he actually got busted for. So first question was, did you cheat? Second question was the substance you cheated with EPO? Now, one of the things you get with blood doping is you do get an increase in your blood thickness, because there's more red blood cells in it, and that puts a strain on your heart, and it could cause permanent cardiovascular damage. But a lot of athletes will tell you that they will make that trade. They've actually talked to athletes, and they've done surveys, anonymous surveys with athletes, and they would ask them questions like, if you could cheat without getting caught, if you can cheat and be the best at your sport for 10 years, the best, like LeBron James in basketball, and Tiger Woods in golf, and if you could be the best at your sport for 10 years, but you would die within 5 years after that, would you do it? And like 2/3 of the people said yes. They would make that trade because of the fame and the fortune. Their kids are set for life. Their family's set for life. They can do, they'll get all this money. They can, but in the fame, they'll be remembered forever. That kind of thing. So 2/3 of the athletes said yes, I would cheat now. With the risk or with the certainty, it's like a certainty you will die within 5 years. They said yes, I would take that deal, and so that's something that is very, very common in sports, is people cheating even when they know that long term it could be a very bad thing. Now the EPO is something that's you produce it naturally, so everybody's going to have EPO levels. It's just they know how, they have a certain threshold that if you're above that, they're going to think you're cheating. Or everybody has levels of red blood cell production, right? But if you're over a certain level, they're going to think you're cheating. If you're abnormally high, then they're going to think you're cheating. Or even testosterone. You have a testosterone level, and if you're above that, then they're going to think you're cheating. So they do have a line. They do have a line that if your EPO levels are above that line, then that indicates that you're probably cheating. Red blood cells don't live very long. This is the last part here. Red blood cells don't live very long because they can't repair themselves. Remember, they have no nucleus, they have no organelles, they can't repair themselves. And so they only live about 4 months. They put 120 days as the maximum lifespan. So that's, by the time it gets there, it's old. Because repair, or what aging is just accumulation of damage, cellular damage over the course of time. And so for the human body, you know, it may take 70, 80 years before that accumulation of damage gets to the point where it kills you. But that accumulation of damage, you start to feel the effects of that like when you're in your 30s and 40s. That's when the aging process starts to catch up with you. That damage has been accumulating over years and years and years. Now your body repairs what it can, if it can, but still though, that accumulation of damage eventually catches up to you, and that's what causes the decline in our health, in our body, in our functioning, all that. And it usually starts about late 20s, early 30s is when you start to first feel the effects of aging. Well, red blood cells can't repair themselves at all. So they accumulate damage a lot quicker. They age a lot quicker than a typical true cell. And so they only live about 4 months. And then by the time they're 4 months old, they're old. They don't work. They're useless, or they're actually causing more harm than good when they can't transport oxygen. They're just taking up space, so to speak. And so what they have to do is they have to be removed. So all the time, you're removing red blood cells from circulation. About the liver and the spleen are the two organs that are responsible for removing red blood cells from production, from circulation. Now, the good thing is that you're not done with it, though, because what you're going to do is you're going to recycle what you can, and you're going to reuse what you can. And even the stuff you can't use, you can still do something with it one last time. And this is one of my favorite stories about how your body doesn't waste anything. It's the whole waste not, want not type deal. Your body will get every possible function that it can out of something. The beautiful resource, our ability to use resources and get everything you could possibly get out of something. So red blood cells, what we'll do is we'll take the old red blood cell. It's done playing its role as a red blood cell. We'll take it. We'll break down the hemoglobin, the protein subunits. And so we'll break down the alpha globin and the beta globin. We'll break it down into amino acids, and we'll use those amino acids again to build other proteins. So we'll actually recycle, so to speak, the amino acids. Then you got the heme group. You take the iron out, and you store it away to use again. And so you'll use the iron again. So you'll use the amino acids that make up hemoglobin again. You'll use the iron to again, that makes up the heme group. Now, the rest of the heme group, without the iron, you need to get rid of that. Okay, that's actually a sort of a waste product. So what your body will do is it will convert the heme group, minus the iron, it will convert the heme group into a substance called bilirubin. And then bilirubin gets added to a substance called bile. Now, bile is a substance produced by your liver and gallbladder, or it's produced by your liver and it's stored in your gallbladder. But you'll actually use bile to digest fat in your food. So bile will eventually make its way into your GI tract. So you remove the red blood cell, you break it down, you use what you can, and then whatever's left over gets converted into bilirubin and gets added to bile. Then bile gets deposited into the GI tract at the small intestine. As it's moving through the GI tract, enzymes will convert the bilirubin into other things. One of the things that bilirubin gets converted into is called urobilinogen. And some of that urobilinogen may make its way to your kidneys and come out in your urine, and that's what gives urine its yellowish color. If the urobilinogen stays in your GI tract, it gets converted again into a substance called stercobilin, and stercobilin has a brown color, and that's actually what makes your poop brown. So when you look at your urine, your urine should have some color to it. That the color they call it urochrome. Chrome means color, urochrome. What makes your pee yellow is basically the heme groups from your red blood cells being removed from the body. They got converted into bilirubin, and then they got converted into urobilinogen, and then they got converted into urochrome. And then when it comes to the poop, no matter what you eat, usually, no matter what you eat, your poop comes out brown. And in fact, if your poop came out in any other color, you would think something's up. The brown of your poop is the heme groups that are being removed from your body. Because remember, you got to remove millions of red blood cells from circulation every minute of the day, because one drop of blood has 5 million red blood cells, right? And a lot of them are old because they've been in there for 3 or 4 months. So you're always constantly removing red blood cells, and you got to get rid of that heme group. So you make it into bilirubin, it goes into the GI tract, Some of it eventually makes its way to the kidneys, comes out in your urine, makes your urine yellow color, and then the rest of it travels through the GI tract and eventually comes out in your poop, and it comes out as a brown color. So that's why urine's yellow and poop is brown. I probably won't ask you a question about number 19, but you do have to know a few things about number 18 on your notes. You have to know that the liver and spleen remove red blood cells from circulation, and that the heme group is converted into bilirubin and eventually makes its way into bile, and then you use that to digest fat. So even when the red blood cell's done, you still can use everything. You still use the heme group for bilirubin, put it in there for bile, and then bile is used to digest fat. So your body's really wonderful at. I love how the body doesn't waste anything. It will use something, and if it's done doing its first job, then it will use it to do something else. And that's what happens here with red blood cells. So if anybody ever asks you why is poop brown, now you have a good reason. You could say that, well, your body has to remove millions of red blood cells every day, and those red blood cells have to be added, components of the red blood cells. You can even mention the heme group. The heme group of red blood cells gets added to bile. It gets converted into bilirubin, added to bile, and then it comes out in your feces, and it's what gives your feces its brown color. You're seeing the excretion of heme groups from your body in both the color of your urine and the color of your stool. And so there you go. All right, that was a long video, I know, but that's the longest one. The next video we'll do leukocytes, and then we'll do platelets.